So, hi, this is Andre again. Today I'm talking about a topic that has been on my list for quite a while now. And I've been asked to do that for quite a while now. So, here it is. How does the video output on the Commodore PET actually work? Stay tuned. So, what we're gonna see is we are going to look at all the 5 different types that Commodore produced that have a different circuitry for the video output. We look at the schematics, so there's a technical deep dive, so don't worry, you get a summary on front, and then you can stay if you want and have a look at the deep dive. And especially the question, what does it have to do with the killer poke, and why is there snow on the screen on the first one? So let's look at the 5 models first. We have the original one, the 2001. It has 40 characters per line and 25 lines on the screen. So it's got a fixed video timing, which is actually NTSC compliant. There's 1 kilobyte of video RAM, and it shows that snow. I'm going to show you later. Then we have the so-called dynamic PET. Those are the first evolutionary stage, so to say. They have a new keyboard, full-size keyboard. The tape is gone. Full-size keyboard. The tape here is gone, and they have still have the fixed timing. But they also have no snow on the screen. And we'll talk about that later in this episode. Then we have the 4032 and the 8032, which are very similar. Actually, the 8032 came out first in one revision that was only capable of doing 80 columns per line. But then they produced a universal, so-called universal board, more or less the same, but they had instructions and options to put in those chips that you can only you can use it as a 40 column PET model. So the same board, 2 options, very nice for Commodore, saving some costs here and having 2 options in the model. They introduced the so-called CRTC, which is the 6845 or 6545 CRTC chip that is also used in a number of other video cards that you know, for example, from the PC scene and other home computers of that time. It's a very flexible chip, but we'll talk about that in a follow-up episode. And same, this is the 8296. It's in a way an 8032 with a 64K expansion, but they completely remodeled the board. So it's actually got 128K of RAM. You can use 4K of that. It's still got a CRTC timing. Yeah, it's very nice machine. So I really like it. It's one of my favorites. But it has to wait for the next episode. So let's look at video output. We're going to talk about video output today. So let's talk about video output. If you look at the screen, let me move me right there. You have these characters that are displayed on the screen line by line, and each character consists of a number of so-called raster lines. In this case, we have 8 raster lines per character, and we have a number of lines per screen. And then this is the area where the actual data is being displayed. And then you have the so-called horizontal retrace period or the vertical retrace period, where there is nothing displayed, but it gives the CRTC, the actual CRT tube, time to readjust the electron beam that's going onto the screen to light that pale green or white dot on the tube. from the right side of the screen back to the beginning of the line, from the end of the line to the beginning of the line. And there's one for the horizontal and one for the vertical part. And we're going to look into more details in that also later. But just typically for that period, you start with coordinates 0, 0, x 0, y 0, with the first pixel of the first displayed character. And then you just count to the end of the line, and when the retrace is done, it starts here again. It's not like today where you have, say, it's not like today where you have, say, the origin of the screen somewhere over there, and then you have some offset until you actually do the screen. So let's look at the original PET. Using all static RAM. That means all the RAM, not just the video RAM, is static RAM. It has 1K static RAM video RAM. It uses 1K by 4 SRAM chips. So actually, 2 variations of the board have been made, some for Commodore specific RAM chips and one for standard RAM chips. Those RAM chips have an access time that is appropriate for 1 megahertz clock frequency. And that video is created by logic circuit. There's no video chip, as in the later models. So when we look at the fixed timing of the original Commodore PET, we see that when we start here, this is actually memory hex 8000 32,768. I can very quickly say that in German, but not really in English. So we have 40 characters on the screen. We have 25 character lines on the screen. We have 32 character lines total, and then a half one to get to the video timing, to get to the NTSC video timing. I'll try to introduce some concepts here. There is this video on signal. This is one signal that will play an important role later on in the schematics, and this is active during the whole time, during those 25 character lines. Actually, 25 character lines by 8 raster lines means 200 raster lines here, and then we have 20 raster lines here in the bottom blank. Then the vertical drive signal needs to be created for the monitor, and you can see the timing here on the right. This is also 20 raster lines, and then the top blank, which is actually, it says top blank because it's actually on top here, because during vertical sync the monitor actually moves the electron beam up to the top again. So, but as I said, counting starts by convention, and in these days with the first displayed raster line. So the top blank is here basically on the bottom of the screen. We have this H display on, horizontal display on. This is also a signal that's important later on. This is active exactly during those 40 characters on the horizontal or on the raster line, where there actually something happens on the display. And then we have the right blank, we have the horizontal drive, H drive signal, and then we have the left blank, as I said, similar to the top blank. This is actually, you have to imagine that on the left hand side. What is interesting is, if you look here, the timing of that signal is interesting. The horizontal drive for those video monitors needs to be 20 microseconds for the retrace and 63.5 microseconds for the actual display, which in the end ends up 64 microseconds if you look at the schematics later. So if you look at that in more detail later, you can see that the horizontal drive actually starts somewhere here, and then moves on and actually ends somewhere here where already something is already displayed. So what does it mean snow on screen when accessing screen memory? And this is actually something that has bothered people, obviously. And Commodore has made something in the ROM of those machines that tries to avoid that. So we'll have, and there has been a lot of stuff going on talking about the killer poke that has to do with that. So why is that snow? Because the video memory only has a 1 megahertz access time. So if you have the video trying to read data to be displayed, and you have the CPU trying to write or something to screen RAM or read something from screen RAM, and both are running actually at an access time of access frequency of 1 megahertz, they can't do both. And the CPU has priority over the video. It's not like in the Commodore 64 where the CPU is halted when video needs to access main memory and doesn't have enough time and whatever. That's another story. The CPU is not halted, it just overrides the video access. And that means while there's an CPU access on the video RAM, and the video circuit is trying to read something from that RAM at this time, it's going to get back that value that the CPU reads or writes. And that's what you see as snow. So this is my original PET, made in the USA, but still 220 volts. And it still has the personal electronic transactor, not like the later models where in Europe they sold as Commodore business machines. And you see the chiclet keyboard, you see the built-in tape. And if you open it up, we can have a look inside. So this is the board. You can see here is the RAM. Here are the ROMs, which are all 2 kilobyte ROMs. Here are the I/O chips. Not exactly sure which one is which. The CPU, VIA and 2 PIAs. And there is the character ROM. And all the other glue, most of the glue, we will have a look at the board layout and schematics later, make up the video output. So let's switch it on. Uh-oh. There you go. That's not good. Na toll. As you've seen in the previous part, I actually did test the snow on the screen, but when I switched it on and after I had prepared the camera, you've seen that this pad has gone broken. But luckily, I don't know when I'll have time to look into that to repair it, but Dave McMurtry from Commodore International Historical Society was so very kind to record some of the footage for me. What you can see here is a small program that prints or pokes values into the screen memory without taking care of whether the display is on or off, and you can really see the snow coming on the screen where the CPU gets priority over the video output. So what consequences did this have? So when Commodore decided to wait for the video output, they have put in this test on the video on signal in the output routine, and let's see how that looks like. So let's write a little program. This is actually a very nice timer that you can use that counts screen refreshes, which is yeah, very appropriate here, I guess. So let's print hello world 400 times and then print ti. So let's see, we have that one, and now we can run it. The screen flashing, I think, is a Vice artifact. But we can see it, we have about 300 screen refreshes. So I now enter the poke. Sorry, 458,62. So what it does is it sets that bit that is being tested to an output bit. So it's always 1, and the routine will never wait. Now, do you want to see how that works? Lots more flickering here, which I think is a Vice artifact. But look at this, almost 3 times faster, just for that little test. And then, of course, people found out quite quickly, and thus this poke was used in games, for example, where it doesn't matter if you have snow on the screen, but you rather want to have a quick reaction time of the machine or printout and so on. And this will have some ramifications on the newer pad with the CRTC that we're going to have in a follow-up video, where it suddenly became the killer poke. So how did Commodore prevent the snow? So let's have a look at the schematics. You see here, which is the I/O section of the dynamic pad. Actually, you have that video on signal that's coming in here, and this video on signal is connected to this I/O pin here, port B5 on the VIA chip. And in the code itself, when you write something to screen, there is this: we load the value from that port bit, from that port, and if it's not set, which means if it's set, which means the video is on, which means it's in the 200 raster lines that actually show something, it loops back to itself. And only when it finds out, okay, I'm outside of that active video area, data is being written to the screen. Now, what about the blanking? And while in this one, this is a nice schematic because it's kind of well ordered. It's well drawn, but it's the follow-up version. If you look at the original version of the schematic, we see this here. There's this blank TV, which is basically a reuse or the same as the and or identify output for the IEEE 488. So if you go back to the original schematic, we can see here's the and or identify out, and that's it. There is no connection to the video. But in the original pad, if you change this line, that blanks the TV. And that's what the editor ROM is doing to prevent too much snow while scrolling, because scrolling takes too long. You can wait for the inactive video area, but then you have a certain amount of cycles, and then you may do the check at the end of the inactive area, then your scrolling runs into the active area and so on. So to prevent any kind of snow here, the screen is actually blanked. So let's get back to the details, and we look at the theory of operation and go into the technical deep dive. You can stop here, or you can follow me through the Let's look at the theory of operation. There are a couple of components. I've drawn a block diagram for those components and how they are connected and used. So let's have a look and I'll give you an overview. We have the horizontal timing. This creates the horizontal display on signal, which is basically the 40 characters on screen that are actually displayed, whereas there is valid data to display. It also creates the horizontal drive, the horizontal sync signal for the monitor. There's a load shift register logic that creates a pulse when the shift register that takes the parallel data from the character ROM to the shift register and loads it in there, and also does the address counter increment. So this is horizontal timing and character timing. The address counter is quite interesting, because if you look at the video output, we can see here that every character consists of 8 raster lines, and because this circuit does not have a buffer like the VIC2 that, you know, in a bad line reads in all the character data for the whole for all the characters, and then only needs to pull the character ROM information from the bus during the actual display. In this situation, in this schematic, the video output has to read the actual character value, say A for A, hex or 65, I think, 66, 62, and so on from memory, and then select one of 8 rows in the character ROM, one for each of those raster lines per character. And so it has to, the system has to read the first byte, the second byte, and so on until the 39th byte. This is done 8 times, and then you read the 28th byte until you get to the 79th byte 8 times, and then you go to the 80th byte, and so on. So this is what the address counter and the start of line hold register does. The address counter counts this address, and at the end of each raster line, when horizontal display gets off, it's reloaded from the start of line hold register. So the start of line hold register for the first character line has the value 0. For the second character line has the value 40, then 80, and so on. How is that start of line hold register updated? In the last raster line of a character, it's actually set to be transparent, which means the address counter value, which goes up from in the first character line from 0 to 20 hex to 7 and then to 8, or 40, 39 and then 40. In the last raster line of a character, there's actually a line going here. This is set to transparent, so it gets updated on the fly. And then when the 9th raster line is displayed, the start of line hold register has the value of the last +1 character of the first character line. So this is has the value 40, and that's where the next 8 raster lines are being read from. So that's very ingenious, but there's nothing else. When you look at the video on the mode and video on and read drive, this is the only information that gets into the vertical timing. And the vertical timing has 4 modes: vertical drive, top blank, video on, bottom blank. You can see that here: video on, bottom blank, vertical drive, top blank. So those 4 modes are being iterated over, and when we see here, the mode only gets the input from this end mode condition, which is called the next signal. And this signal depends just on the value of the start of line hold register and the address counter. So we're going to go into more deeper detail later on. So the reason for this is this address counter is actually reused. So in this part of the video on, it actually counts until it gets to the end of the displayed character, which is 200 raster lines. Oops, sorry. And then in the bottom blank, vertical drive, and top blank, it counts 20 raster lines, which is actually 2 character lines plus a half. And then we get 260 raster lines with 64, that's also going to be important, 64 microseconds for a raster line, and this is 16,640 cycles per screen, which is almost NTSC compliant. So that's very ingenious, reusing that address counter. I'm sure it reduces the chip count a lot. When we have the address selection. We have to switch between the video output and the CPU address, which is done in the address selector. We have the data buffer for access from the CPU. The output from the video RAM goes to the char ROM directly. Here we have the raster lines per char counter. It has a fixed timing, it counts 8 raster lines per char. And as I said, it tells the start of line hold register when it's in the last line. And then we have all the information we need. We know, okay, this is, we read from the video RAM, we read the value, say for A 65. We look into the character ROM, we are in the 1, 2, 3, 4, whatever raster line of that character. And then this information gets output from the character ROM, gets into the shift register, is loaded into the shift register, and then it's inverted on bit 7, because the character ROM actually only holds 128 characters, because so they could use a 2 kilobyte character ROM for 2 character sets, because they use the 7th bit as an invert bit. This is delayed because this all takes time here, and is then used to invert the actual video out. So let's look at the schematics of the video output. What you can see here is, and that's the very nice thing, this is all the whole schematic of the video output for the original PET. So it's all on one sheet. It's kind of messy when you look at how the lines, the signals are meandering around, and it took some time to find out where everything goes and so on. What I've done is I've tried to map, or I mapped the building blocks of the video output onto this schematics, as we can see here. So we have all the different components. We have clock generation, we have the horizontal timer, we have the counter and address hold register, next condition, mode, address switch, RAM, data bus buffers for the CPU, character ROM, shift register, and output. So it's all there, and we're going to go through all of those in detail. But before I want to go into detail of the schematic, I would like to show you, because this is all, I would like to show you how this evolved in later stages of the PET, because in later stages this all has been simplified by the use of the CRTC controller chip, the video controller chip. And if you look at this, all those parts that are shown here in gray now have been replaced by the CRTC chip. And this of course makes it much more flexible, because you don't have to fix timing and so on.
You can all change the end conditions for the raster line counter. Say you don't have 8 but 9 or 10 raster lines per character. You could have a larger video memory and so on, and all that stuff. The rest of that stuff still has to go into some discrete schematic on the circuitry on the newer PETs as well. Now looking at the board, this is the board for the original PET, and I've marked a couple of components here. You can see the system RAM, the system ROM, the CPU, the PIA for the keyboard, PIA for IEEE, VIA for user port and stuff. And what I've marked here in red is basically what is needed for the video output. So you can see that this is really a considerable amount of board space that is used for the video output. When you look at what will be replaced with CRTC logic, so this is all what goes into the CRTC in the later revisions. And now let's look at the different components. So let's look at the different parts. And this is going to be a deep dive, and I try to make it as quick, but still hope you get all the information you want. So clock generation. If we look at this part of the screen, I zoomed in here a little bit. You can see this is the 8 megahertz clock, which is actually a crystal. This is a typical crystal circuit. Then there is a driver for that, and that is used in various places on the board. And then we have a counter, which is 74LS93, which is interesting because it changes on the falling edge and it's not synchronous. So there is ripple between the different outputs, but anyway, just a detail. And there is a JK flip-flop. JK flip-flop, if you don't know them, look them up. They are a very basic form of logic gates. And the main thing is if J is set, when the clock goes down, the output Q is going up. When K is set, when the clock goes down, Q is going down. So it's in a way as a clocked RS flip-flop, in a way. So and here you can see the output of this one is going somewhere over there, but the main thing here is phi0, which goes to the CPU. And it's synchronized with the 8 megahertz clock and taken from the 1 megahertz clock generated here. Let's look at the horizontal timing. Horizontal timing, as I said, we have the horizontal display on. We have the right blank, we have the left blank, and we have the horizontal drive. And we need to create this output. So those are generated with this logic. And if you have a closer look, we can see here, this is the, this is actually a 1, 2, 3, 4, 5, 6-bit counter. So it's part of that chip that divides by 8 to get the 1 megahertz from the 8 megahertz clock. And this is the second part of the same chip. And this is another divide by 16 counter, the same type, LS93. And then there's a JK flip-flop. The reason for why they use the JK flip-flop is probably because they have both the normal and the inverted output available. Then we have here, we have the display on signal generation. So we take signals from that counter, and when Q here is on, then display can start. When not Q is on, then display can go off. You can see here the display on, display off. Those are all those are used here. We'll have a look at the timing on the next slide. And then we have the horizontal drive creation. So let's look at the timing. So we have that. You can see here the pin output C9 pin 11. This is actually the one here on the 1 megahertz. That's the input to the horizontal counter, and we have the different counter values. This is all you see here, the 4 bits for the counter. We have these JK flip-flop. Then we have the logic gates that create the end. The ended signal for the display on. And then we have the horizontal display on, and this is 24. This goes low when this value here is high, and then we have a falling edge on the clock here, and it goes up. I guess it's the same when the second one here is when the other one. This is the J input, and the clock goes down here. And then we have a delay, just a delay, which is interesting for the vertical drive. So the vertical drive actually reaches into the displayed area. Well, strange, but works. Next section, looking at the load shift register control. This is interesting. This creates a pulse here on that signal that goes to the right here, this is actually a pull-up. You have to look at, there are a lot of signal lines that actually are driven by a pull-up resistor and don't have any kind of drivers attached. It makes sense to put them in a schematic, but sometimes you have to try to ignore them when when you look at and trying to understand that. So that's at the 1 megahertz clock. There is this pull-up on J, and K is 0. So if the 1 megahertz clock goes down, Q will always go up. When Q goes up, then there is this NAND of the output with the 8 megahertz. So on the next 8 megahertz pulse, this actually activates the reset circuit. So it's really only a very short pulse, which is synchronized with the 1 megahertz clock. When you look at the diagram here, we have the 8 megahertz clock. Oops. We have the 8 megahertz clock. Sorry. So we have the 8 megahertz clock. We have the 4 megahertz. We have the 2 megahertz, the 1 megahertz output. That's actually, this is only, you know, it is how it works in principle. It's not an exact diagram, because you actually have to look up the data sheets for the delays, ripple delays between the different outputs and so on. But as you can see, when 8 megahertz, when 1 megahertz goes down, which is later than this 8 megahertz going down because of the ripple effect, the JK flip-flop goes up. And when the JK flip-flop is up and the 8 megahertz clock is up, then this NAND triggers and puts that signal down again. And this is the signal that actually loads the shift register. Now let's look at the mode stuff. You have the video on. We have the bottom blank, vertical drive, top blank, which are the different 4 modes in the system, and it also has to create the vertical drive, which is more than 200 microseconds, and then you have that 16,660 16.66 milliseconds, which is then basically NTSC timing. So this is created by this vertical mode V drive. And this is an interesting is the two JK flip-flops that follow each other. You can see them, they have the same clock. If J is high, Q goes up. And then the second one, J is high, then Q goes up. But then if this Q goes up, and the next time K is up, so this one goes down. So it's not a counter, but instead it shifts the phases like so. It goes from 0, 0, 0, 1 to 1, 1 to 1, 0. You need to understand that, because then that yeah, it took me a while to grab that. It's not a counter, so from vertical drive it's not followed directly, or from video on there's not vertical drive directly following because of the overflow, counter overflow. No, it's this kind of, it's a sequence that is created. And then depending on if both outputs are 0, then we have the vertical drive, and if both outputs are 1, we have the video on signal. The next signal, which is coming in here, we'll talk about that in a minute. But just want to make sure you understand how this is actually switching between the different vertical modes, switching between the different sections of the screen. You can see here the video on is exactly on during the 200 raster lines that have actual display data, and then there's a vertical drive. So let's look at the address counter. So we have the 10-bit counter for the video address. We have the 8-bit hold register for repeated reads, like I described before. So the actual clock here is, if you see that, maybe you can see that, is coming from the load shift register. So every time we have the pulse on the shift register, this is the first bit of the counter. It counts 1 up. And there's one peculiarity with the JK flip-flops: if both inputs are high and you have the clock running, the output alternates. Goes from 1 to 0, 0 to 1. So this is basically a counter. This goes into the next one, which has the same setup. J and K inputs are both set high. And the reason, and that's basically all. Those are the first 2 address bits, and the reason for that, because why they can do that, because all the numbers in the timing are divisible by 4. So those actually don't really matter much. You don't need to reload them. And then we have 2 4-bit counters. You can see here that on display on, this signal is going to the load input of the counter. So when display is off, basically display on is 0, those counters are transparent. So the outputs give exactly the value that's on the input. So this is basically loaded from the hold register, because when display on goes on again, it then has that exact value. And then we have the, this is actually the video on signal. I'm sorry, this one. And that clears the counter. No, actually, this is the next signal. Yeah, let me have a look. Yep, this is the next signal. Every time, this is the next signal. Every time the mode changes from the 200 raster lines for characters to the 20 raster lines for the bottom blank, to the 20 raster lines for the vertical string, to the 20 raster lines for the top blank, the counter resets with this one. And it's counted actually from output from those 2 bits here that's coming in here. And here we have the load register. This is actually replaced with a more modern 373 or for part in the follow-up model. Here it's a 74-100, which is a transparent ledge. So, and it's transparent when we have the last raster line counter for each char is coming in down here, and we have the next value. That the next signal is because that is when everything has to be reloaded or restarted from zero. So this also has to be cleared then again, and it's cleared because the counters are cleared and the output is going to the hold register. And the nice thing here really is that during that last raster line of a character, the counters are happily counting from, say, 0 to 39 and then to 40, and the hold register is set to transparent. So it's loading every time the counter changes. It's loading, basically setting the new value, and once we have the next raster line, the counter has actually the value 40 for the next character line. Very nice. So some more example here, because we have that 2 bits of the address, the lowest 2 bits of the address that are implemented as JK flip-flops. The hold register is actually bits 2 to 9. 2, 3, 4, 5, 6, 7, 8, 9. Yeah, 8 bits. And so the hold register holds 0 for the first character line, 10 for the second character line, 20 for the third character line, and so on, because it's all divided by 4. And we have the address counter restart every time the mode changes. So how does the mode change? We have to look at the next logic, which is the next conditions, and some control logic. Going to have a look at this one. So this is difficult to read. That's why for this part I'm actually going to the schematic of the follow-up model, which is basically the same. And you see that here we have these lines. Here is the next signal coming out of the logic. The signals finally have some nice names, like video on, or not 200 lines, not 20 lines. Let's have a look at a little bit larger. What we can see here is, first let's look at the not 200 lines. So how do we compare that? How do we compare the value of the counter of the hold register with 250, which would be the one that is basically start of the line, raster line after the displayed character. So basically the overflow into the not seen, into the bottom blank. And what they did was they optimized it away really a lot. Because you can see here, this is just 4 ANDs. So this is an AND, and this is, if you could take these two together, it's an AND. This is an AND. So they use 5 signal lines of that, and when those are active, then it signals, okay, we have the 200. We have finished the 200 raster lines. And then it looks at, okay, we are off the horizontal display, so we can actually do something with it. When you look at the counter, it's actually quite ingenious, because the counter only, or the hold register only holds specific values. It starts with 0, 10, 20, and so on. Goes to 230, 240, 250. It's all like the video address divided by 4. And once it gets to behind the last displayed character, it goes to 1000. And then you only need to AND these signals. They could have used this one or that one, but one of those is enough. And then that's it. Very, very, totally simple timing. When you look at the 20 raster line, so I've tried to
put it here on and focus on the 20 raster line, what we see here is this is basically a schematic of the simplification. So we have the displays off. We have this RA9, which is raster line per char is in the second half. And we have the counter before. And when you know 20 lines only off, and then it's only off screen here. So what's interesting is they are using the counter bit 4 and not the hold register bit 4. The counter bit 4 goes high already in the second character line, because if you bit 4 is 16, value 16, you multiply by 4. As I said, the counter counts basically streaks of 4 characters, and this is already in the middle of the second character row. But this is not 20 raster lines. It's one character line, which is 8 raster lines, and then half of it is only 12. 8 plus 4. Interesting, but it's evaluated only off screen. But at that situation, the counter is loaded with the register value. So this is they could have used the hold register before instead. And this means that this is actually then from the hold register bit 4, which is, as we said, we have 0, 10, 20, and the 20 is the 16. Has 16 plus 4, so on the third character line, the hold register bit 4 is set. And then we have that when we are half into that character line, which is this, we'll have a look at this in a moment. We have 20 raster lines, and then that gives that signal. So this creates the next signal, so we know when the next mode starts. This is actually the C6. Is this one here? Is the last one here that ends with the horizontal display off. And then we have the JK flip-flop coming from the 2 MHz line to synchronize with the clock, and then we have the next going to the mode, and then to reset the raster line counter. Let's have a look at the raster line counter next. Raster line counter is here, so that's actually pretty simple. We have the horizontal display on, which is the clock input to the raster line counter. So every finished raster line, the counter counts 1 up. So it puts in the next raster line of that character. And then we have that output here, 3 bits of output that are NANDed together with display on, so to say. Let me have a look. Yeah, to actually set the hold register to transparent. So also what we have here, this is the one that goes. This is the uppermost bit of that counter, and that goes high in the second half of the character, and the fourth raster line, and that goes to the 20 lines detection. So let's have a recap. So what we've seen so far is all these parts, which are, once you get to understand them and you try to, unwrangle all the different signals here and lines, it's actually quite an ingenious video circuit. And if you look at, if you take out the load shift register and the clock generation, this is actually what the 6545 or 6845 CRTC does. Now let's look at the rest that's still missing. Looking at the RAM access, so those are those parts. We have the switches,
that switch between the CPU address bus, BA6, BA1, BA2, BA3, and so on, and the video address here, which is coming from the counter on to the left. Those are the feedback lines to the hold register. The output of those address lines go to the video RAM. They are actually selected all the time, but they are synchronous. They are based on the Phi2 clock, at least the 6550 RAMs. There are models with other chips. I haven't had a look, but they should be pretty similar. The read-write line needs to be switched as well, because the video always reads, only the CPU writes. So this is coming from here, and this is actually interesting, because it's read not write multiplied by not select E, or select which is when reading, when one of those is low. So select 8 is actually a positive logic, so it's high when the CPU selects the video RAM address. So when the video RAM address is selected and read not write is high, then we have pin 1 low, which is going to the read to the CPU. And when we have the RAM read minus write, only the CPU writes. Once we have a write signal here, this goes to the other side of the buffer, and then pushes the data out, takes the data from the CPU into the RAM. As I said, interesting here, there is this connection with selecting the E address space, which doesn't matter because it's always selected here with the with the video RAM. So yeah, that looks very strange. Maybe that's a remnant of some discussions they had. As I've seen in later schematics, there's a jumper to move the I/O area to hex 8800 instead of the current E800. Probably they have been discussing that there as well, but yeah, doesn't really make much sense. Could have used read not write. Let's look how the character ROM and the pixel are created. So we have the character ROM, which is the 6540 chip here. It's always selected. You get the raster line count and end condition are the lowest 3 address bits. We have the address bits from the data bus, from the RAM data bus. They are address bits 3 to 9, and then we have the graphic line, which is coming from an I/O chip, where you can actually switch between the uppercase, lowercase, and the uppercase graphics mode. What we notably see missing here is the SD7, which is the inverse bit. It's not going into the character ROM, so you're saving half of the space for the character ROM. The output from the character ROM goes into shift register. This has the load bit from the schematic, from the circuit we have discussed before. Has the 8 megahertz clock. This goes the pixel out. It's very, very nice. This invert. It's not an XOR or something that might give some timing problems. Looking at when you invert that, but this is a symmetric output. So the 7th bit is delayed here by let me guess 1 or 2 clock cycles, and then the positive and negative bit is set here to the end, one with the positive and negative output of the shift register, and then those are NANDed, and then they go into the video output. This is, I think, display on here. and some other sort of stuff here. So what does the timing look like? We have the 8 megahertz clock, we have the 1 megahertz output, we have the shift register load, we have the Phi2 clock, we have the RAM address, and what we have here is the RAM address must be active and valid when Phi2 goes high for the RAM. So the data goes out 200 nanoseconds after that, and then the character ROM has an access time of 300 nanoseconds. I'm not sure I got the right data sheets. It's not exactly clear, but I think that should be right. So that the data is available once the shift register load pulse is coming. Then the character ROM out has the data for the shift register. So, summary of the original PET. You have a fixed video timing, you have all TTL logic except for the RAMs and ROMs. You have quite some optimization to reduce the chip count. The hold register is only 8-bit. The next condition logic is very much reduced to really the bare minimum. And the address counter is used for off-screen timing because you can use it multiple times to count different things. The 1 megahertz RAM does not allow for time sharing video between video and CPU. So the RAM will see either the data that's written from the CPU or will output the data that is read by the CPU, and this exact data is going to the char ROM. So when you access the video memory while video is active, that's when the snow happens. Now let's have a look at the follow-up model pad. Those have a 9-inch screen as well. They have the large keyboard. They have dynamic RAM for the main memory, but they still have 1K video RAM, which is an SRAM. But this SRAM now is available for in 2 megahertz access time, and we still have no video chip, but the logic basically is very much the same. Because we have 2 megahertz video timing, there's no snow on the screen, which is cool. So let's have a look. In the schematics, the same principles of operation apply. It's spread out on 2 sheets, so we'll look at the differences only. The general timing. This one is somewhat different, actually quite a bit different. We have a 16 megahertz oscillator, 16 megahertz base clock, and we create 8 versions of Phi clock, which are delayed by 1/16 of the actual clock, and then we can use logic to generate any signal we actually like, and we'll see that later. So what we have here, for example, we have the new video latch control that takes the Phi2 phase F, but the inverted one, and ends it with the Phi2 phase H, the real one. I think I have a timing diagram later. Here are some DRAM control signals, which are only, of course, needed for dynamic RAM machines. The refresh address generation, horizontal timing, display on mode is basically the same. The only thing is this one, which is an extra logic gate, probably thought to improve the timing, but the rest is exactly the same. I said for the horizontal timing, this is all the same. It is basically all the same, but there are some tabs basically to use the output of that counter for refresh addressing for the dynamic RAM of the main memory. So so the actual circuit is not different, but the output is reused in this case. The load shift register is using the shifted clocks as a source now to create the pulse for loading the shift register. So we have, and again, this is really only very sketchy diagram. We have phi 2 here. We have the various delayed and inverted clocks here. Phase A, phase B, phase H, phase F, inverted phase F, and so on. And then we can load shift register. If we go back, you see this is a data flip-flop now. It's not a JK flip-flop anymore, but they started putting in data flip-flops here. So it's on the rising edge of the clock, which is actually phase 2A inverted. This gets high, and then when we have phase 2B gets low, it's cleared again. Phase 2A inverted gets high, so the load shift register pulse gets up, and then phase 2B goes down, so there's our load shift register pulse. And the same here for the video latch. The video latch is something interesting. That's an extra part that we need to look into because of the new timing. Video counters, basically the same, except the first bit is actually taken from reuse from the refresh counter. Hold register, next mode, condition, RAM address selection is basically the same. Only the address switch is based on a clock, not on a CPU select anymore. So because the RAM is fast enough for 2 MHz, so on the phi 2.0 we have video access, phi 2.1 we have CPU access, which is very similar to the VIC on VIC 2 video chips. Select logic. There we have different CPU read and write signals for read and write access. But that's just an update. And again, the RAM read not write signal is going through the selector here, because during RAM it's only during video output it's only reading. Okay, let's look at the last one. Video out. Those are basically the same. We have the raster line counter here. You have the character ROM here. We have the shift register here. We have the data bus buffers here. You see the different control inputs. We can see that this diagram has been really improved regarding clarity, regarding signal names and so on, and drawing quality. So by the way, all these schematics are available on the web. I'll put the links to the schematics in the description below. So then, delay for inverse band video latch. This is actually something new, and the reason for this is because when we have that RAM here, it outputs the data during phi 2 is 0, but we only have the shift register load here at the end of phi 2. So we have to actually latch that data into a register, and that's that, or into a latch, and that's what is used here. Okay. Also here, there's only one data latch. It's not a JK latch anymore for the bit 7, because this is actually stored here in this latch. That's to adjust the timing. And the timing here is we have phi 2, we have the video address RAM, the video RAM address bits goes from the video address, CPU address, video address, CPU address, depending on the system clock. We have the data from the video address that's coming out of the video RAM that goes into the latch. we have the video latch control, which is here. When it goes up, the latch takes the data. Yeah, right. Okay, no, it's transparent latch when it's up. It's not on the signal change, but when it's up, it's transparent. So it takes the video RAM data, puts it onto the latch output, which is the same as the character ROM address, and then we have the output, and then we have the shift register low. So today we've had a look at the first two variants of the PET video output. Both are the ones that have the pure TTL circuit video output, which make them kind of interesting. Other machines of that area did have TTL-based video output as well, the Apple II, for example. So this is it for today. There will be a follow-up video. I can't promise that the follow-up video is the very next video, but there will be a follow-up video, and we're going to look at the other three different types of video output. That should go a bit faster because all the video timing and so on is done in the CRTC chip. I may even put in the bonus looking at the color pad from Steve Gray. Okay, hope you liked it. Thanks for staying so long if you have. Thanks for watching, and see you next time.